Hello. Today we will introduce the Modbus client component in HIL Control Center. With this component, the HIL device can also act as a client in a Modbus network. You can now define Modbus client behavior in Schematic Editor and it will operate autonomously during simulation runtime. This represents a simpler and better integrated alternative to Python API and HIL SCADA implementation of the Modbus client side, as no scripting is required for implementing this. Moreover, this leads to improved Modbus communication speed and better integration with the rest of the model. The Modbus client component available with version 2021.3 of HIL Control Center only supports 16-bit registers. However, 32-bit and 64-bit registers are planned for subsequent releases. You can find more information about how this component and how it is implemented in the HIL Documentation Hub. For this tutorial, we will be going through the Modbus client and server multi-HIL setup example model, which can be accessed in the Communication Protocols section of Example Explorer in the HIL Control Center software. Microgrids play a steadily increasing role in energy delivery systems, and the need to model and test their control systems has grown with it. In order to exchange information and control components inside a microgrid remotely, it is necessary to properly set up communication using a standard communication interface. For this reason, including the real communication layer is critical when building high-fidelity microgrid models. In this example, a Modbus network is used to control and monitor the energy storage system. This model consists of a battery energy storage system connected to the grid and a passive load that can be connected or disconnected via SCADA. The Modbus Server component is connected to the energy storage system, performing high-level monitoring and control. The Modbus client, on the other hand, is implemented on a second HIL device, performing remote monitoring. First, let's start with the Modbus Server configuration. The Modbus Server and client components must have matching register addresses and ports in order to properly exchange variables between each other. While it is possible to have many client components in the schematic communicating with the server, in this example we will only show communication between one server and one client. Here we have a closer look at the Modbus Server. In this example, the analog variables from the battery generic component inputs are connected to the input registers port of the Modbus Server component. Also, two binary variables are connected to coil inputs. These are the enable variable, a digital output describing the converter state, and the MCB status, which reports the information about the state of the main circuit breaker. At the output of the Modbus Server component, we have the variables we want to control in the model. Those are controlled from the Modbus client requests. In this example, the Modbus Server receives data from the Modbus client and outputs it to the model, in this case the battery storage system. Commands to enable and disable the grid connection, reset the alarm, change the converter operation mode, and set voltage, frequency, and power references are included in this example. There is also a SCADA input that allows you to select if the model is controlled through HIL SCADA or the Modbus client component. Now we are going to explain the Modbus client component setup in more detail. By entering in the properties of the Modbus client component, the first thing we must do is to set the proper IP addresses in order to connect with the Modbus server. The server IP address field must match the Modbus server IP, while the client IP must differ. In the requests field we have all the requests the client sends to the server, whether time or event-driven. In this example, we selected multiple requests and divided them into groups of variables. The read address, write address, number to read, and number to write must exactly match what was defined on the server. For this example, we will use read input registers, read coils, write multiple registers, and write single coil function codes. With those, we can control and properly monitor our energy storage system through the Modbus TCP network. Let's go to SCADA to see how this model functions in real time. The SCADA is divided in two main parts. The first widget group shows the SCADA interface with the first HIL device, which comprises of the model and the Modbus server component. In this first part it is possible to control the model directly from SCADA. The second widget group displays the second HIL device where the Modbus client is implemented. Every main widget group here has a subpanel inside of it. In this example, they are opened in windowed mode by default. The subpanels make it possible to monitor and control the battery storage system, whether by SCADA commands or Modbus client requests. After the model is loaded and executed, the server will wait for connections from the client. If Modbus client is online and connected to the Modbus server, a message will display that Modbus is online. It is possible to interact with the battery system. You can interact with it and enable or disable grid connection, change operation mode and set power. And change voltage and frequency references. Thank you for joining us for this general introduction to the Modbus client component in the HIL Control Center and the model example provided to evaluate it.